Hi, I'm Ben-Yaakov. This presentation is entitled Behind the Curtain of LDO Stabilized Switched Capacitor Converters, and also a review some aspect of a paper that deals with Supercapacitor Assisted LED driver. There are some related videos that I've put here the link to, and also I'm going to put the links at the page of this video that we are now watching, so you can click on it and get to them, and they are giving background of issues that I'm not covering in this presentation. So the question that I'm posing at the beginning here is, if I have a switched capacitor converter and then I have an LDO, is this a good idea, and what does it do? And in fact, there have been some claims that by this the ripple will be lower at the output. This makes sense because the LDO has a quiet output, so this issue is really makes a lot of sense. Now there is another issue that has been claimed, that there is a better efficiency this way. You can get better efficiency, and therefore it's a good way to go. So I'm going to concentrate on this second issue, and let me start off with an LDO. Now, what is the efficiency of LDO? I'm showing here a very simple LDO. This is a P-channel MOSFET for low dropout. We have an error amplifier sampling the output, comparing it to the reference, either directly or with a divider perhaps, and then operating the switch such that it'll control the current to maintain the output voltage to be constant. So what is the efficiency of this unit? Assuming that this current of the amplifier is low as compared to I in and I out, then I in is equal to I out, and then P in is I in V in, here it is, and I out V out is P out, and therefore the efficiency is P out over P in. And since I in and I out are equal, then we find, which is well known of course, that the efficiency is V out over V in. So if V in is high voltage, then the efficiency goes down because the drop on the LDO, which causes of course power dissipation, but we can look at here from a sort of global point of view. Now, what about a switched capacitor converter? Let's have a look first of all on the operation of a typical switched capacitor converter, and I'm showing here a divide by two. In this case, we have the so-called flying capacitor connected in series with the input and output, and then it parallel to the output. And let's assume that the voltage on this capacitor is half V in, and we'll see that it will be maintained. So when we have this connection here, this is V in over 2, and this is actually in the opposite direction to V in, so therefore the V out here is V in minus V in over 2, which is of course V in over 2. And in this case, we are just connecting the V in over 2 in parallel to the output, which is again V in over 2. So this is a divide by 2 converter. Now the model of a switched capacitor converter, of any switched capacitor converter, is this equivalent circuit, which looks like a Thevenin equivalent circuit. We have a voltage source and then an internal resistance. This voltage source is representing the topology. In fact, it is equal to some n times V in depending on the topology. In our case, n is 0.5. There are some other topologies that give you times 2 or divide by something or times 5, etc. So this is the voltage source, topology dependent, and which determines n. Rs, however, has to do with the internal resistance, also with the capacitance, and it can be shown, and it is sort of explained in the reference video that I've mentioned, that if you plot this resistance is a function of frequency, you get something like that. This is a switching frequency. You get something like that. At the low frequency range, the resistance is 1 over switching frequency times capacitor, capacitance of the capacitor, the flying capacitor, or flying capacitors. In a more involved topology, you may have a number of capacitors. And at this end, it's proportional to the resistance of the switches. Why is that? Because at low frequency, the current of the capacitor is like a exponential down slope, and it ends before the end of the switching instant, while in the case of the high frequency, the timing is very short and the current is about constant. So in fact, you see here just the resistance, and the RMS here is much higher than the RMS here, and this is why the resistance, the equivalent resistor actually represent losses, becomes higher and higher. So this is the model, and now I'm turning to something which is not very well recognized, and that is the current transformation of a switch capacitor converter, which turns out to be stronger than the voltage gain. Because in the case of the voltage, there is a target voltage, which is N times V in, but as you load the output, of course, there'll be a drop here because of the internal resistance. Not so in the current case. And let's see why is this. If, just for the sake of explanation, and I'm doing the explanation in a very simple and intuitive way, not to go into too many equations here, let's assume that RS is very small, this RS. So the output here will be actually VT, the target voltage, so to speak, the N times V in. Now the losses are going to be small, so therefore the output power is equal to the input power, no internal losses. Input is I in V in, output is I out V out, dividing the two, and knowing that V out is N times V in, we find that I out to I in is 1 over N. Okay, the voltage ratio is N times V in, while the current ratio is 1 over N, which makes sense because it's a constant power. So when you multiply the two, you should get 1. Now, it is important to realize that the current ratio does not change with loading, okay? And first of all, I give here sort of an explanation, and then we'll see a couple of examples. The explanation is the following. In this system, there is no current going to ground, because you have a capacitor which is charged and discharged, charged and discharged. There is no current that is flowing this way. So all the current is coming in, and then there is some current coming out. Doesn't have to be the same, because you can have like capacitors in parallel or in series. We'll see it in a minute. But the point is that there is no current going this way, and the relationship, therefore, between the input and output should be the topology dependent. So let's have a look what happens in this divide by 2. In this case, when the switch is in this direction, we have a current I in going out. The I in and I in, this is this current. This is the average input current. The second timing, the second state, there's no current, no instantaneous current here. And the current is coming from the capacitor, and since we charge and discharge by the same amount of charge, therefore the current, the average current coming in and coming out must be the same, and therefore we see that we have here twice I in. So this is exactly what we have seen, that I out over I in is 1 over N, N is 0.5, so this is why this is 2. Now let's take another extreme example, and for those who still don't believe what I'm saying, that if I take a short here, okay, just a short, I'm shorting out the output. What happens? Well, let's assume that we start with a capacitor which is with 0 voltage on it. Then it will charge here to the input, and this is the amount of charge coming out. And then you connect it to the short, so it'll discharge completely. So once you get Q from here, once you discharge, and then again you get twice the charge, and then of course times frequency is current, and you get the same ratio. So this is a very strong relationship, the current transfer ratio. So how can we use it? We use it to have a very quick result for the efficiency, because if P in is I in times V in, and P out is I out times V out, and I out over I in is 1 over N no matter what is the loading, therefore the efficiency P out over P in, which is this ratio, I out over I in is 1 over N, and N times V in is the target voltage, and we see that the efficiency is V out over the target voltage. That is the voltage at open circuit, and that in the case we have discussed is like 0.5 of the input. So this is a very easy way to look at it, and again it is a universal result. It's really independent of the topology, independent of the switching, the exponential relationship or whatever. It must hold, because I'm talking about the total input, the total output, the relationship between them. They must obey what we just said. So now I'm coming to the question of what happens if I have an LDO following a switched capacitor converter. Okay? Now, if I have a current coming into the switched capacitor converter, the current coming out is 1 over N. But the current coming out here is the same, because we have seen it, that the input current and output current of an LDO. So now if I do a calculation here and here, it'll be exactly like in the switched capacitor converter. And if I'll go through it, V out times the current at the output, which is 1 over N times I in, we get the same result. So the efficiency of this system is V out over the target voltage of the switched capacitor converter. This LDO does not make any difference. Does not make any difference. We'll see that the switched capacitor can help a little with LDO, but as far as the losses go, it is still V out over the target voltage. Now, if there is no switched capacitor converter, then obviously V in comes into here, and then the efficiency is V out over V in, and obviously in certain cases it could be lower, because, for example, if you have 24 volts, N equal to 0.5, they divide by 2, it will be 12 volt after the switched capacitor converter. Suppose this is 10 volt, then the efficiency is 10 over 12. But without the switched capacitor converter, we have 20 volt here, 20 volt here, and the efficiency is much, much lower. So the switched capacitor converter can bring down, lower the voltage, and by that improve the efficiency of the system. Now what happens if I put a capacitor here? Well, really nothing, because in terms of efficiency, because it may smooth the waveform, but avoid the pulsation. But when you talk about the current coming in and coming out, there's no DC current through the capacitor, so it really doesn't matter, and therefore it is exactly the same. Now what happens if I just load the switched capacitor converter with a resistor, no capacitor? Okay, in some topology this could be a problem, because they might have a pulsating output, but let's say in the case of the divide by 2, it's pretty constant, because you have either the series connected capacitor or the parallel connected capacitor to the output. So you'll have a little ripple, and if we sort of neglect the ripple, then again the efficiency will be V out over the V target. That's it. There's no difference what's the kind of load you have here. It could be current source or whatever. What matters is the voltage here. The current ratio, as we have said, is the same. The voltage may drop by loading, changing the switching frequency, for example, but this thing holds no matter what type of load you have. So what are the conclusions here? Number one is that the efficiency is independent of an LDO connected in series with the switch capacitor converter. Of course, the system efficiency can be improved if you put a switch capacitor converter that lowers the voltage so that the LDO will see a lower voltage. That's obvious. Now, the same efficiency is obtained without an LDO. This is very important. That is, if we don't have an LDO, everything is the same. So I can actually adjust the output with the switch capacitor converter and get the voltage that I want. Maybe it will be more noisy, but as far as efficiency goes, it will be the same. Because the efficiency, again, if this is the same target voltage, then the efficiency is again whatever V out you will have over VT. One way, by the way, to do a regulation of a switch capacitor converter, going back to the model, is changing the internal resistance. You can do it by changing the frequency, okay? And this will change the internal resistance, and by that you can actually control the output, but the efficiency, again, will depend on whatever voltage you eventually got divided by the target voltage. So now I'm turning to a paper. Actually, it's one paper in a series of papers that was written by these authors. Not same all the time, but some of them are same authors. And it has to do with supercapacitor assisted LED actually driver. Let me first of all point out that using supercapacitors in switch capacitor converter is very good. No question about that. And the reason is that at this frequency range, the resistance, the internal resistance, is dependent on 1 over Fc, and if the capacitance is large, and in supercapacitor could be 1 farad and even larger, 1000 farad, then the internal resistance is small, and therefore if you work, say, in open loop, if you load the switch capacitor converter, then the drop will not be that large because the internal resistance is low, and also the efficiency will be kept, because if the voltage doesn't drop, the efficiency is kept to be high. So no question that supercapacitors in switch capacitor converters are good. Well, they may be expensive, but they are good in terms of performance. However, there are some claims here which sort of are questionable. In this paper, they are showing actually it's a switch capacitor converter, although they call it a different name. And what it is actually there are two channels here. There's a load, which is the LED lamp assembly. This is actually not LED lamp, it's an assembly with a driver inside, which could be driven either way. There's positive or negative voltage. It's like unit that's supposed to be connected to an AC, I suppose, and therefore you can feed in DC either way. And if you look at the operation, it is a divide by 2 switch capacitor converter. In one phase, you connect the input in series with the capacitor to the LED, and then you connect the the capacitor to the LED by itself. This resistance represents the line or internal resistances of the circuit. And then they say here that if the DC equivalent resistance of the LED lamp is much higher than the parasitic resistance, that is, this resistance is much higher than this resistance, then most of the energy wasted in the RC charging loop is utilized by the LED lamp. That is, efficiency will be kept high because this resistance is smaller than this. Well, this is, of course, in general correct, but this is not the reason for it. The reason would be what is the voltage on the lamp as compared to the target voltage, which is half the the voltage here. And then they are showing this LDO connected to the, again, divide by 2 switch capacitor converter. Here we have the source in series, and here the capacitor feeding the LDO. And then it says that it minimizing series dissipation. And there's an explanation here which says the following. Let me just go over it, although it's written here. And it says the following: if you have a simple case of a voltage source feeding a capacitor, you lose half of the energy. We know that. And then if you have a voltage source which is charging a capacitor through the load, which is the case here, then there's no power loss. Well, this is incorrect, because it has to do again with the ratio of the voltage on the load as divided by the target voltage of the circuit. And this question of charging a capacitor and losing energy is just irrelevant to what we are talking about. And it's not an argument to prove that you have a lower efficiency, which you don't, because the efficiency again will depend on the voltage here divided by the target voltage, which in this case is half the input voltage, period. And the same thing goes here. The efficiency will be a function of the voltage of the lamp divided by the target voltage, which is in this case also half the input voltage. So I think there is a problem here with the statements, and this is what I actually wanted to bring up. So this brings me to the end of this presentation. I hope you found it of interest, and perhaps it will be useful to you in the future. Thank you very much.